तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, we have been discussing the high electron mobility transistor. Most of it we have discussed how it works, what are structures that are there for gallium arsenide based devices, and also on indium phosphide based devices. Now, today I will continue on that little bit on a structure known as pseudomorphic HEMT, and then we will go on to the topic on bipolar transistors. In fact, just to remind you, I am showing this structure again, that is the indium phosphide based HEMT, where structure is common, similar. On the top you have got a heavily doped layer, in this case it is aluminum indium arsenide, because it has lattice match with gallium indium arsenide, which has lattice match with indium phosphide. So, you have got buffer layer, undoped layer which is a channel layer, spacer layer to improve the mobility, so that there is these two dimensional electron gas does not at all see the dopants, okay, dopant layer. So, that is a spacer layer, then aluminum indium arsenide. Okay. Now, this we saw there are various versions are there, because this type of structure gives a slight problem with the breakdown voltage. So, what they did was change this top layer with indium phosphide, which has problem with Schottky barrier contact. Then another structure which was put, keep the top layer like this, instead of gallium indium arsenide put indium phosphide. Okay. Now, the problem there is lattice match is there, but the mobility of indium phosphide is low. So, you get high on resistance, all these problems are there. Now, here in this structure slight problem is because of high aluminum content. So, the moment you have high aluminum content, you get of course good delta is here even compared to the gallium arsenide based structures. So, what was suggested or what was thought of was modify this entire structure, go back to gallium arsenide based devices, but you would like to have gallium indium arsenide because it gives better mobility than gallium arsenide. So, the another structure called the pseudomorphic HEMT. Here what is done is, this is not indium phosphide based, this is gallium arsenide based. You have semi insulating gallium arsenide substrate, you can get it with very high purity, still you can put a buffer layer, so that any of the defects do not get transported onto the undoped layer, and this layer is indium gallium arsenide. You can see that you do not use that indium 0.47, but you use indium 0.15, mostly gallium. It is gallium rich indium gallium arsenide, but still it is mobility better than that of gallium arsenide, because indium arsenide has got very high mobility compared to gallium arsenide. Indium gallium arsenide will be somewhere in between, depending upon how much indium you put. You do not want to put fully indium, because the band gap is low. Now, here this band gap will be close to about 1 or so, and the gallium arsenide is 1.43. So, you got now yourself a structure which has gallium arsenide, indium gallium arsenide, undoped gallium arsenide, silicon doped gallium arsenide. In fact, you can replace this top layer with aluminum gallium arsenide also. You get better delta EC if you like, because higher band gap you can get here. Okay. So, this top structure you will see in many places, instead of gallium arsenide put as aluminum arsenide, aluminum L gas. What is the problem with this? Right at the beginning we were telling, you must have the layers which are lattice matched to each other. So, if I put gallium arsenide layer as the channel layer and the doped layer L gas has a very good match, If I use indium phosphide substrate, gallium indium arsenide has a good match provided gallium is 0.47. Now, what we are talking of is indium gallium arsenide, which does not have lattice match with gallium arsenide, grown on gallium arsenide. So, this layer, if it is very thick, it will have lattice constant of this indium gallium arsenide. See, if you recall, indium has a tetrahedral radius 1.44 angstroms compared to 1.26 of gallium. So, the lattice constant of indium arsenide is much larger than that of gallium arsenide. When you mix indium arsenide and gallium arsenide, lattice constant is in between. How much closer it is to gallium arsenide depends upon how much less indium is present. So, here it is close to gallium arsenide, but not as much as gallium arsenide. Okay. So, this layer could be defective, but it so turns out that if you make this layer very thin, that does not have those dislocations or the defects. So, in fact, this is a defect free layer, but it is a strained layer. That is what is called as pseudomorphic layer. Okay. It is not truly a defectless layer. There are no defects like dislocations, but it is a strained layer. So, its properties will not be exactly like indium gallium arsenide, slightly different. Okay. Now, let us take a look at what happens. So, this is a layer which gives you the high mobility. It also gives you the ability to gallium arsenide grow on the top of that. This also has got to be thin. So, when you grow a layer like this, a defect free, physically no defects, but it is a strained layer, that is why we call it a pseudomorphic layer. Okay. It is not genuinely defect free. Okay. When you say it does not have defect free, it does not have dislocations, etc. So, just let us take a look at the structure here. I will go back to the device afterwards. We are talking of now a layer which does not have lattice match, grown on a substrate layer. So, this is the substrate layer in which it has certain lattice constant. It could be gallium arsenide or some lattice constant. Now, on the top of that you grow an epitaxial layer whose lattice constant is more than that of this. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, here there are less number of those lattices. Okay. That is, spacing between the atoms is more. So, if this entire layer is grown on that, the tendency of this layer, for example, if it is gallium indium arsenide, is to take this structure. So, if you have to grow on this, there are two ways. One way is this structure. See, the bottom layer has the lattice structure of gallium arsenide or the material 1. The top layer has, on the top surface, it has lattice structure of this epitaxial layer. But in between you can see finally it has to go join hands with the thing to complete a structure. So, you can see these bonds are stretched out there. There are some other bonds which are not formed at all. There are more number of atoms here, less number of atoms there. So, this atom does not have a bond there. This is a defective layer. Similarly, this atom does not have a bond there. It does not have a neighbor, because all the other neighbors are occupied. Neighboring atoms forms bonds with these atoms. So, these two different colors or sizes are shown. It can be gallium indium arsenide, a compound, that is why it is shown like that. So, but the top layer now, when you keep on growing, it will have a layer which is defective, or alternately, if the top layer is very thin, what happens is this bottom layer exerts stress on this top layer, pulls the atoms together to collapse it down. So, you can see here all the atoms are aligned with respect to that. Number of atoms here are same as this. What has happened is the lattice constant here, or the spacing between the atoms compared to the original atom here, is reduced. This is because as you start growing the layer, initial layer will not have defects. The initial layer will take the same lattice structure as the substrate, because the stress that is brought in from the substrate will affect the thin layer. This layer will not get affected because it is very thick. The layer which is grown gets affected. Okay. It experiences the force of these atoms, and these atoms compress the lattice. Okay. And this layer is the strained layer. So, what this it is this layer which we call it as the pseudomorphic layer. As you keep on growing, if this layer becomes thicker and thicker, then that is it has its own ability to come back and pull back into its original lattice structure. So, what we are telling is, you grow a layer whose lattice constant is different from the substrate till you reach some critical thickness, 20 angstroms, 30 angstroms or about 40 angstroms, depending upon the relative difference in the lattice constants. It will still have the single crystal structure without defects, without dislocations, and that layer is the strain layer, and that is the layer which you call it as pseudomorphic layer. And it has the mobilities which are high. In fact, this has peculiar properties which sometimes give even higher mobilities than the unstrained layer. So, okay. But if you keep on growing thicker and thicker layers, then this pulls back to its original size, its minimum energy position, and the lattice breaks here. That is a defective layer here. So, once this was realized, people said, why not make devices like this? I do not need a very thick layer to make the channel. All that I need is a thin layer. Okay. So, that is how they made this type of layers. They grew indium gallium arsenide on gallium arsenide, though there is no lattice match. This is a strained layer. Okay. And then of course, on the top of that you can put gallium arsenide. This actually gives better performance in terms of the mobility. It also gives better performance in terms of the band gap of this layer compared to indium, which is 0.47, because the band gap is slightly higher. Now, you may have slight problem with the electron confinement, because the gallium arsenide band gap is 1.43. Gallium arsenide band gap is 1.43. This may be about, you can calculate by substituting the formula that I gave, about 1 or so, or 1.1. So, delta E c here may not be much, 2/3 of the difference. So, if there is 0.4, 2/3 of that will be 0.8 by 3. So, it is slightly less than 0.3. You want better electron confinement, what you can do will be switch over from gallium arsenide to aluminum gallium arsenide. It is no difference between gallium arsenide and aluminum gallium arsenide as far as the lattice constant is concerned. But as far as band gap is concerned, it depends upon how much aluminum content is present. The advantage of changing out aluminum gallium arsenide is you can get a higher band gap. You do not have to go all the way to 0.3, 0.4 aluminum content, because this band gap is smaller. You will get delta E c or delta E g much higher than between gallium arsenide and indium gallium arsenide by changing out aluminum gallium arsenide. You can remain within safe region by putting aluminum content which is not very high. 0.1, 0.2, you do not have to even go to 0.3, still you will get better delta E g, and because of that better delta E c, higher electron concentration, higher maximum current that you can get for the given device. Okay, so that is I just thought I will point out this to you, because in many places you will come across people talking of strained layers, strained layer epitaxy, and pseudomorphic layers or devices. All that I am summing up is here is it is a thin layer. So long as this layer is thin, you can grow epitaxy layers without defect. You can't grow thick layers of epitaxy. You can't think of growing 10 micron epitaxy. Can't think of growing 1 micron epitaxy, but you can grow 20 angstroms, 30 angstroms, 50 angstroms of that order. In fact, this is the principle which is used for making heterojunction devices with silicon germanium. Okay. Now, you can see, you can talk of not merely compound semiconductors with the gallium arsenide indium phosphide, that is 3,5 semiconductors. you can talk of compound semiconductor devices with silicon itself. Okay. You may not talk of high electron mobility transistor, but you can talk of bipolar type of transistors, okay, in the case of silicon germanium. See, the problem with silicon germanium is germanium core band gap is smaller, but if you mix silicon with germanium, you can get a band gap which is in between germanium and silicon. Both are indirect band gap semiconductors. So, you can make a heterojunction device with silicon and germanium, provided you can grow silicon germanium. I think I am with you. We will come back to this silicon germanium little later. Silicon on silicon germanium on silicon. This type of structures you can grow, provided this layer is very thin. Because if this layer is thin, even though this lattice is not matched with the silicon lattice, this will be strained layer without defect. So, you get mobility is as good as silicon germanium or even sometimes better, the strain layer. So, this is silicon X germanium 1 minus X, silicon X germanium 1 minus X. X equal 0 is germanium, X equal 1 is silicon. This sort of structures are possible. Today, it is a very popular device or material, silicon germanium and silicon for high speed devices. I think I will have occasion to talk about that little later during the course of the coming few lectures. But very popular for not for high electron mobility transistors. Neither of them have high electron mobility. Silicon 1500, germanium 3600. Silicon germanium will be in between, but you will see that this is suitable for making bipolar transistors. Okay, now let us just go back and see. So, you can see there is an opening for silicon germanium, silicon based devices. Silicon guy is very happy, because silicon is cheaper than gallium arsenide, much cheaper than indium phosphide. So, if you can make devices with silicon and heterojunctions with silicon, then that opens up another area which has been very popular for high speed. Okay. In fact, I will come back to this particular thing. Many of the industries look into this type of devices and have been working on that. Okay, now that means actually let us just take a look at, so that almost right now we close the chapter on this field effect transistors, with which we have discussed MESFET or JFET or both, same performance. Instead of Schottky barrier you put junction, it becomes JFET, and then high electron mobility transistors with gallium arsenide based, indium phosphide based. All these you can classify as FET. MOSFET, we are not talking of MOSFET in the case of gallium arsenide, indium phosphide, etc., because we have discussed and said native oxides are not good in those devices. They lead to lot of interface state densities. Silicon, we are fortunate that native oxide actually gives very good interface state, very low interface state density. Okay. But instead, we will talk of MIS type of devices. I will come back to that. Right now, let us leave that, because that is one area which we have been working. MIS is the counterpart of MOS. If you are putting metal insulator semiconductor, metal oxide semiconductor, put some insulator, deposit some insulator. I will come back to that, particularly with gallium arsenide based devices, MIS type of devices, MIS field effect transistor with silicon nitride. In fact, that work has been done in IIT Madras in great detail, the PhD by one of my students on MIS field effect transistors using gallium arsenide. Okay. We will come back to that afterwards, but in the meanwhile, let us see whether you have to dwell with the FETs at all. Just this is summary of what we have said, that is this particular aspect I have just mentioned orally. Schematic representation of possible means of growing lattice mismatched materials. That is the footnote for this. Unstrained case, both materials retain their bulk structure, resulting in misbonded atoms at the interface. This is unstrained. strained cases, thinner or more elastic, the thinner layer gets flexible, compresses in the plane of growth, in that direction it compresses. That is what we have shown there. This gets compressed in that direction, elongation in that direction, that gets compressed, so that it matches with that. So, that is what we have shown here. Let us leave this now and go back to this, compare how will the FET. Do you have to totally ignore other type of device like bipolar junction transistor? Is there any merit in bipolar? Why we are taking a look at it is, one of the things is silicon germanium has come up in a strong way with silicon with the possibility of making a bipolar junction transistor. Number 2, if you take a look at the fastest logic circuit, that is the emitter coupled logic, bipolar transistor. So, this gives us a feeling maybe we should take a second look at the bipolar transistor. And what are the problems in bipolar transistors? What are the merits of bipolar transistor compared to FET? If it has no merit, do not have to look into it at all. It so turns out that the bipolar transistor is the one which was invented first before the FET was invented. But the search was for FET. Shockley, Bardeen, etc. They were working on searching for field effect transistor. They were working on getting a working FET, but then the problems which landed up led them to bipolar transistor. And for several years it ruled the market for about 2 decades. 1970s the FET came, but all the time bipolar transistor has been coming back with vengeance, I would say. You can see here, if you have high electron mobility transistor etc. here, what do you have here? Let us compare the FETs and the field BJTs. In the case of field effect transistor, it is a majority carrier device, unipolar device. Between source and drain you have the channel. All the charge that is present is in the channel region, that is very small. Q is equal to C into V. That is a small thing. So, turning on, turning off of the device is easy compared to the bipolar transistor. Bipolar transistor, you take a look at the bipolar transistor, NPN, you can put N plus because emitter, and then the base, and then you will have always a N plus layer put. This is always present, so that first reduce the series resistance, you put N plus layer. Now, that is the forward bias. I just put, for sake of illustrating, I will put this diagram, not that it is common base, ultimately in the active region this is reverse bias, this is forward biased. So, here you can see in the active region you have got the carrier concentration here like this, that is x. This is carrier concentration is like that, and on the emitter side, of course, there is a small transition region is present. Here, of course, there is a transition region, and from here you have got Pn0. These are all stored charges. This is stored charge. So, when you turn off the device, this charge from here must be removed, and if the base is open during turn off, the charge will decay by recombination only. That slows down the process. So, if you turn off, for faster turn off, you must have the base driven the reverse direction to draw this charge. This is one of the problems. How do you reduce this charge? Reduce the base width. This is the active region. In fact, in the emitter coupled logic circuit, it never goes into saturation. In the TTL, you prevent the transistor going to deep saturation to better speed. Now, if the transistor is saturation, how does it happen? This is active region. So, that is the stored charge that we are talking of, stored charge here, stored charge here. You must reduce this width, reduce this width, all the bits must be reduced, reduce the stored charge, and then saturation. If you allow the device to go to saturation, both emitter base junction and collector base junction are forward biased. Then what is the thing? You just put it like this. I will put the same diagram, but with this like that, forward bias. What is the structure now? What is charge distribution? That you remember when you go into discussions later, this is the carrier distribution charge or electrons or and holes. Here that is like that. What about in the base? Collector is forward bias. Carrier concentration here is up, carrier concentration here is up. It is almost like that. In fact, if the base width is small, that is linear. But forward charge here, say, a tremendous amount of charge here. If it goes into saturation, remove the charge, you must pump out the charge from that region, base region, by reverse draw of the current in the base. What about here? When the forward bias, the killer is here also. That is, I have a small transition region in all the cases, of course, which I have not shown here. Then from there, this is n p of x, p n of x, and this is p n. Injected holes, forward bias, p n junction forward bias, holes are injected there. That will be another thing. Now, you can see the problem is compounded when it goes into saturation, but if you use emitter couple logic, you can cut down at least that stored charge here. You can cut down this charge, but still you have this charge, stored charge. If you take the MOS transistor, it is much smaller, in the form of majority carrier. Now, let us see what other problems. So, this is one of the dreaded problems with bipolar. Transconductance. Let us see then if there is merit on the bipolar transistor. Transconductance, what does it depend upon? MOSFET or HEMT or MESFET. All of them have ID equals mu n C. The key C can be C oxide or CS. Okay. C, I put it as C, okay, but let me not put it as that general term, into W divided by 2L into VGS minus V threshold square. In the case of MOSFET, it is V threshold, MESFET is V threshold, in the case of HEMT, we call it as V off. It is actually threshold voltage. This is C, is C oxide or CS. Or CS. So, I think I have some problem with this. Okay, CS. This depends upon oxide thickness. This depends upon, in the case of MESFET, the n layer thickness. In the case of HEMT, the top aluminum gallium arsenide layer thickness, doped layer, CS. Okay. So, you actually want to maximize that by reducing the oxide thickness or by reducing the layer thickness, L gas layer thickness or in the case of MESFET the gallium arsenide layer thickness, that we improve. Okay. Now, what is GM? GM is equal to okay. So, that is the transconductance. Okay. That is the transconductance that we have, and then here you can see that the transconductance is proportional to width and VGS minus VGS. It is a square law device. Transconductance can improve. To improve that, you have got to improve this particular. Of course, this increase only linearly with the VGS. W, you must have bigger and bigger ratio WL to have a higher transconductance. Why do you need higher transconductance? You need higher transconductance because that gives you ability to charge capacitive loads easily. Okay. You must have higher current for a given change in voltage. For a given change in voltage, higher current you can have if WL ratio is large. Device becomes bigger. This was one of the problems with power devices. You have got big W by L ratio. Now, what about bipolar BJT? BJT IC is I naught e to the power of you change the collector current by changing the emitter base voltage. When you change the emitter base voltage, emitter current changes. Correspondingly, you have the change in the collector current. Now, you can see what is GM. Output current change for a given change in voltage. That is actually equal to IC by VT. Delta I by dV is again IC by VT. So, you can see it depends on the current. In fact, this changes exponentially with voltage. So, the MOSs or the FETs are square law devices. These are devices which change large change in current for a small change in the input voltage. High transconductance devices is bipolar for the given size. Of course, you can always argue I can improve the GM by making WL ratio large, but that occupies a lot of space. That is not the theme of today's integrated circuit. You want to have smaller devices, that is possible with this thing. So, that is one of the advantages for higher speeds. That is why you prefer bipolar. Bipolar, though it is a slower device by itself, okay, it is faster in this ability to charge subsequent capacitive loads. So, in an integrated circuit between bipolar and MOS type of devices, bipolar circuit is faster because of its ability to charge all the capacitances. Ultimately, as I keep on shrinking the device size, it is a capacitive load. Where does the capacitive load come from? Not merely from the next gate, it also comes from the routing capacitance. That rules the performance completely. That is when it governs the performance, and then you must have ability to charge these capacitors fast. So, that is one of the benefits of this. So, highest transconductance is BJT per unit area, depends upon the collector current, which exponentially depends on VBE by VT. Okay. Cutoff frequency. Now, basically, if you want to talk about the cutoff frequency, what is the cutoff frequency of the transistor? 1 by transit time, omega t is 1 by transit time. Okay. So, the transit time depends on channel length. Transit time is length divided by velocity. Okay. So, that is one. So, length you can reduce to get better cutoff frequency. 1 by transit time. Okay. So, here the base width. Now, this is here that the FET scores a bit, because velocities are high. The velocities in the case of FETs are high because they are transported by drift. Okay. You can have even the saturation velocity, that is what we have been seeing all through. This is where the individual, the actually intrinsic frequency response of the FET is much better compared to bipolar transistor, because for the same channel length, say 1 micron channel length, 1 micron base width if you take, this will have better cutoff frequency, because velocities are larger. Transit time or the cutoff frequency f t is 1 by 2 pi into tau t, or omega t is 1 by tau t. So, this tau t is the transit time. Through the channel, through the device. Now, transit time actually is given by length divided by velocity, centimeter divided by centimeter per second. Okay. So, you can keep on reducing L. Notice when you keep on reducing L, what is the constraint? Constraint is on lithography. Okay. Now, velocity, of course, ultimate limit is the saturation velocity or velocity overshoot effect, all those things are there. This will be high in the case of MOSFET and HEMT, etc. It is very high. That is why you get smaller transit times, higher cutoff frequencies of gigahertz range. Bipolar, please note that you must reduce the channel length, okay, to get smaller and smaller transit times. BJT, this is the MOSFET. This is true for both. Okay. The BJT transit time is what? W squared divided by 2dn, centimeter square divided by centimeter square per second. So, it is second. So, here you can see transit time is reduced by reducing the width, base width. But when you write this equation, what is the meaning, implication? I am not going to derive it, because in the first course you have done it. The implication is that the current transport is by diffusion in the base region. So, when you have transport by diffusion, the velocities are small, whereas if it is by drift, velocities are high. You can reduce this transit time by reducing base width. Okay. So, after all, if this device has to compete with the MOSFET or MESFET or HEMT, you must have ability to, you must keep on reducing the base width. Okay. And you must also bring in the electric field. If you bring in the electric field, this will reduce by some factor. Okay. You can bring in electric field by different methods. Wherever doping concentration variation is there, okay, there is electric field. Wherever there is band gap variation is there, there is electric field. So, this sort of thing in fact is the trick that they have played in the heterojunction silicon germanium transistor, where you do not have to vary doping, you can vary the band gap to bring in the electric field. Okay. I think it will be very interesting to see some of those silicon germanium concepts in this discussion itself. Okay. So, what we are telling is, from the cutoff frequency point of view, you tend to buy the FETs, but when they go into integrated circuits, bipolar has an edge over that. So, you can compete with the MOS or HEMT, etc., to some extent at least in terms of intrinsic speed by reducing the base width, by transporting the carriers through the base with drift plus diffusion. Okay. So, I am just pointing out these things because you want to take a look at that, because it performs better in the integrated circuit because of its better transconductance or smaller size. Most important of all, okay, the most important of all is the threshold voltage. If you see the threshold voltage of FETs, strongly depends upon what? If in the case of MESFET, thickness of that layer, doping of that layer. Threshold voltage depends on VBA minus VP0. VP0 depends upon doping and thickness. Over the entire wafer, the thickness must be same, doping must be same, becomes harder and harder when you are talking of enhancement type of devices, where threshold voltage is VBI minus VP0. You are talking of small VP0. Then small change in VP0 brings in a lot of change in threshold voltage. So it becomes more, this quantity, threshold voltage in the case of FED depends upon the doping and thickness of the layer. In the case of MESFET, what about HEMT? It depends upon VBI minus VP0 again, that is the doping of that n plus layer and the thickness of that layer. You want, of course, to reduce the thickness to improve the transconductance, then you have still deal with thinner layers. Thinner layers, uniformity over the entire 4-inch wafer or 6-inch wafer, it becomes more and more difficult. Maybe with gallium arsenide deal with only 4-inch wafer. In silicon, of course, it is much wider, much bigger wafer. Silicon also you must worry about the doping, because threshold voltage depends upon twice phi f. Threshold voltage depends on doping in substrate in addition to oxide thickness. So, oxide thickness uniformity and doping in the substrate both control threshold voltage. Over a 12-inch wafer you need that uniformity. Okay, this is one of the problems people face when you go to thinner and thinner oxides to get perfectly uniform over the entire wafer. What about bipolar? Where do you have threshold voltage in case of bipolar transistor? People normally do not talk of threshold voltage bipolar transistor. So, in the case of BJT, if you take the IV characteristics of a diode, emitter base junction, IE versus VBE, okay, it is like that, exponential. What is the threshold voltage here? And this is actually equal to IC. IC is approximately equal to IE. What is this quantity? This is 0, this is VBE, and this is the cut-in voltage V gamma. Cut-in voltage is threshold voltage. Now, the cut-in, okay, that is the point at which it really begins to conduct. In the case of BJT, you have a cut-in voltage, which actually can call it a threshold voltage. After all, in the case of MOSFET or HEMT also, current is not 0 when you go to threshold voltage, current is there. Similarly, current is there in that, but it is small compared to operating point. So, cut-in voltage 0.65, 0.7 for silicon, about 1 volt for gallium arsenide, PN junction. So, the moment you fix the material, cut-in voltage is fixed, threshold voltage is fixed. So, that is one of the biggest benefits of bipolar transistor. You do not have to worry about change in the threshold voltage over the wafer. One end to the other end, it will be same cut-in voltage, same threshold voltage. Okay? So, that is a big merit of bipolar transistor compared to FETs. So, to sum up now regarding the benefits of and comparative merits, negative side, if you want to say about bipolar, it is a slower device by itself intrinsically, because of stored charges, switching speeds get hurt because of that, okay, and intrinsically its cutoff frequency is smaller because of the transport of electrons in the base compared to the transport of electrons in the channel. High electromobility, as the name itself indicates, gives you better cutoff frequencies. In terms of merits, transconductance is better, so it can charge capacitors, capacitive loads better. So, in an integrated circuit, it can perform better. So, as an individual, it may not perform well, but as a group, it is a group player, it can perform much better than the FETs. Okay? That is why it still survives in the front end. When you want high speed, ICs, okay, then it is the bipolar that you look towards. That is where this we have to nurture or take a look into the bipolar transistor. Added to that, there is one more technological benefit in bipolar transistor. That was one of the biggest scoring points for several years for bipolar transistors. Even today it is. What is that? Apart from the threshold voltage. Threshold voltage, of course, you worry when you go to smaller and smaller voltages in devices, you worry about uniformity of threshold voltage. So, in the case of bipolar transistor, you do not have to worry at all, it is fixed. What about the channel length? In FET, you have to set out on lithography, depends on heavily depends on photolithography or lithography, why say photolithography, because it can be electron lithography also, on lithography. So, you can see you go in for more and more sophisticated lithography techniques to get shorter and shorter channel lengths. What about BJT? So, that is FET is that lithography dependent. BJT, base width, WB. Does it depend upon lithography? Absolutely no. Is independent of okay. That tells the whole story when people are comparing the MOSFET and bipolar transistor. 1970s textbooks, if you open up and see, it will tell you that MOSFET is lower, because at that time the lithography was 5 micron, 10 micron, that range, 5 micron I think, and the base width that you are going to get is 0.5 micron very comfortably. Okay. See, if you take a look at the base width of the transistor, the N type region, I am just putting this collector, whether talk of integrated circuit BJT or discrete BJT, structure is same, only you take the contact at the bottom or top. So, I will put that structure here. P region N plus, emitter is. In the integrated circuit, you put an N plus layer here, you take the contact on the top. So, now this is the base width. I can make this without resorting to the electron lithography or any other thing. I can go down to 0.1 micron, 0.1, 0.2 micron base width I can get very easily. Even way back in 1970s you could do that, okay, by diffusion, double diffusion, whereas there was no way you could do the MOSFET of 0.1 micron, 0.2 micron technology. Only today we are talking of that after about 20-30 years, because its dependence on lithography, whereas this is depends on WB, depends on WB. W is independent of lithography. It depends upon, if you are doing by diffusion, single diffusion, double diffusion. The diffusion depends upon time and temperature. You can control and control this width quite precisely, control this width quite precisely, or you can implant this region, get the junction. So, this base width you can control precisely by the process, not by lithography. you do not have to depend upon lithography. Okay, that is where actually the bipolar scored in speed in 70s, but it stayed on. Even today it competes with that, because if you do not have that, what if you want to call it high funda lithography, you can depend upon that thing. Okay. Now, let us go back and see. So, this all gives us the motivation to still look at the bipolar device. Now, can we sort out some of the problems that you have set by using compound semiconductors like silicon germanium or gallium arsenide or indium phosphide? What problems? One is, of course, you want to go for smaller transit time, smaller base width. Okay. And what problems are there if you go to smaller base width? How do you realize the transistors? In the case of compound semiconductors, what you will do will be, you will not be doing double diffusion like this. You will go in epitaxial layer, base width doped, and then maybe you can implant dopants. Okay, that is the way you do the thing. So, let us see what are the problems which are there in the case of the bipolar transistor, or how the problems are overcome. So, what problems are? One of the two. So, what we need to do? We need to go in for a modified structure called heterojunction bipolar transistor to overcome some of these problems that are experienced by the BJT. One of the major problems is actually the transit time. So, you must cut down the base width. Okay. If you cut down the base width, what problems do you have? That is what is put down here. For high speed, base width should be reduced. Intrinsic speed if you want to increase. Okay. And this, what is the consequence of increasing base width? Reducing base width. So, let us put that down here. If I put a circuit diagram like this, they see the N plus. I am still showing the circuit arrangement similar to what you have got in the conventional bipolar junction transistor. This is the base, emitter and the base, and of course, you have the collector. If I reduce this base width, what is the parameter which is going to be affected? The lateral width, the current flow in the lateral direction flows in this direction. So, if I reduce this width of the base to reduce the transit time, it is accompanied by reduction in the cross section to the current flow in the vertical direction, in the lateral direction. The cross section is reduced here. If the cross section is reduced, it increases the resistance. In fact, this resistance for the lateral flow, current flow increases. That is the RBB or RBB dash. That is conventionally it is used RBB dash. So, that increases. So, what we will have to do is think of the ways of reducing RBB dash. Think of the ways of reducing the base width, base resistance. That can be done by increasing doping. So, it goes without saying, whenever you have reduction in thickness, you must increase the doping. Now, if you increase the doping in the base, what are the effects which are following to that? Okay. It has tremendous detrimental effects if you increase the doping, but without increasing doping, you can get better performance by moving on to HBT. I will discuss some of these aspects next lecture.